good spirit. And during the last session, we are through with probability, the concepts involved in understanding probability, and the several approaches to our probability. And finally, we landed with a theorem called as Bayes' theorem. So today we will be discussing the next unit of yours, that is discrete probability distributions. And we will be, as because all your probabilities and probability distributions are mostly related to or mostly involved with your random experiments, random variables, and so on. So we will be starting with the random experiment again. So, this will be introducing you to the fundamental concepts of your random variables, probability distributions, and several mathematical expectations which form the core of your probability theory. And of course, in today's parlance, it is your data analytics and data science and data analysis. So, understanding random experiments in the previous class also we are through with. In any random experiment, the experimenter is primarily interested in identify the possible outcomes. Random experiment means the experiment which we will be conducting without whose outcomes are not certain. What will be the outcome? Exactly, we don't know. It may be this or maybe that. That is what is our random experiment. So the experimenter is primarily interested in identifying the possible outcomes and understanding the likelihood of their occurrence. However, merely identifying outcomes is not sufficient. The experimenter is also seeks a systematic way to measure and analyze them. So that means the experimenter will be analyzing, measuring the possible outcomes. That is where your probability concepts and definitions come into picture, or you may say this leads to the need for your probability concepts and definitions. So your probability provides a structured framework to assign numerical values to likelihood of outcomes. So your probability will be assigning a numeric value to the possible outcome of your random experiment. So it helps transform uncertainty into measurable quantity, thereby supporting our rational decision making. So thus probability acts as a bridge between uncertain events and quantitative analysis. Okay, it is a bridge, or it bridges the gap between your uncertainty events and quantitative analysis. So when the focus is a number of outcomes in many practical situations, the experimenter is not concerned with the type of outcomes, but rather with the number of times a particular event occurs. Sorry. For example, instead of identifying individual outcomes, the focus may be on counting successes or failures. In such cases, the concept of random variables and probability distributions become essential. Okay, that means in all the cases, the experimenter is not exactly with the possible outcome, but how many times a particular outcome is occurring in a particular event. That is the measure of concern. That is where our concept of random variables and probability distributions becomes essential. For example, the dice experiment that we had in our last class. Consider an experiment where n dice. We are simultaneously throwing the n dice. Each of the dice is having 6 faces that you know. So the experimenter may be interested in determining the sum of the points appearing on the faces of the dice. So when I'll be throwing all the dice together, it will be one face that will be visible. So the sum of the phases is the interest of the experimenter. So this type of problem is effectively analyzed using probability concepts and distribution of outcomes. So it demonstrates how complex outcomes can be simplified through probabilistic methods. Similar is the case when we are tossing a coin. So that tossing a coin experiment, suppose say I'll be tossing n number of coins simultaneously and randomly. So in that case, I will be getting number of tails and number of heads in each of my toss. So suppose say at any point of time, the experimenter may be interested in finding the number of tails obtained. So here the focus shifts from identifying outcomes to counting the occurrences. So this naturally introduces the concept of assigning numeric values to your outcomes. So when numerical values are assigned to the outcomes of a random experiment, the resulting function is called a random variable. So a random variable provides a mathematical representation of uncertain outcomes. Or in simple terms, you may say your qualitative outcomes which will be converted into or transformed into quantitative data is called as your random variables. So random process and its association, the process of assigning numbers to outcomes is known as a random process, and the assignment itself is referred to as random association. So random process is assigning numbers to outcomes, and assignment of the numbers to the outcome of your random process is itself called as your random association. So this association enables systematic analysis of randomness using mathematical tools. So the result of this process is the formation of a random variable. So once your random variable is defined, then probability, that means the number of heads or number of tails appear, that probability are assigned to each of its possible values. So this complete set of values along with its probabilities, that means whatever values that we are getting, we are assigning to each and every possible outcomes, events that is occurring. That means whenever we are throwing a dice, one event occurs. So whenever we are throwing it several times, each time we may get either a head or a tail. So if we will be counting each of my occurrences, then that complete set of values along with their probabilities is known as your probability distribution. Okay. Once we define a random variable, the probabilities that we are assigning to each of its possible values, that complete set of assigned values of each of the possible values, that together is called as your probability distribution. You may say the complete set of values along with their probabilities is known as your probability distribution. Okay. Then what is the analytical power of your probability distribution? It enables us in analyzing the behavior and characteristics of a random variable. So how your random variable will behave and what are the basic characteristics of each and every random variable that is involved in that experiment, that your probability distribution will enable you in analyzing that. So it provides the basis for computing important statistical measures like your mean or expectation, median, variance, and your higher order movements. So when a random variable is observed repeatedly, its long-term average value is known as mathematical expectation. Okay, long-term average value. So exactly how we will be calculating the mathematical expectation of a probability distribution we are coming in our future slides. So you may say your long when we are observing a random variable repeatedly, its long-term average value, that means the number of times I am observing the behavior of my random variable, then after the number of occurrences, if I'll be calculating the long-term average, then that is called as my mathematical expectation. So it represents exactly expected or average outcome of a random process. So mathematical expectation is really a central concept in your probability and statistics. Suppose say if we will consider our real life applications of expectation, then you may say your mathematical expectation is widely used in practical decision making scenarios. For example, a businessman uses it to estimate their average profit. A medical professional may use this mathematical expectation to evaluate the average success rate of the treatment. Or it helps in forecasting and planning under uncertainty. So in the present day or in modern day data analysis and programming, your random variables and their distributions are used to summarize large data sets. So these summaries provide meaningful insights into structure and behavior of data. So to get the pattern of the data that we have gathered, to make it the you may say data mining and all, to understand how our random variable is really behaving, in that case this particular mathematical expectation will enable you in providing you the insights into the structure and behavior of the data. So in common summary, maybe measures include your mean, median, mode, variance and standard deviation, quantiles, minimum and maximum values, etc. So random variables, probability. So far we have discussed what random variables, probability distributions, and mathematical expectation. These are basically the core concepts, and they build the backbone of your probability theory. So these concepts are essential for understanding your uncertainty and in modeling your real world phenomena and making data driven decisions. And they are widely applied, you may say, in your economics, business analytics, engineering, data science, and so on. So, what are the importance of these core concepts? Why should we go for these things? Because your random variable, you may say, your probability distributions and mathematical expectations, as because they form the backbone of the theory, these are essential for understanding your uncertainty. They are widely applied in economics and business analytics. So, having understood these conceptual foundations, we now move towards our more formal discussion, that is mathematical definition of a mathematical expression of random variables, different types of random variables. So these core concepts, you may say, this transforms uncertainty into insight, enabling informed decision making in an unpredictable world. So random variables. So when we first hear that random variable, it may appear that it simply refers to a variable that behaves randomly. But this interpretation is not exactly accurate. You may say it is not merely a variable, but a mathematical function that assigns numeric values to outcomes of a random experiment. Why it is a mathematical function? As because this variable has got a domain. That means it can take on the values from a specific set, and the output of it is also a value from a specific set of values. So beyond that set, they cannot take any input, or beyond that set of range, they cannot give you the output. So random variable is a function. So each and every function represent a relationship between two well-defined sets. By set, I mean a collection of numbers or elements. So one is your domain, that means the input values, and range is the possible outcomes, that is output values. So similarly, a random variable establishes a relationship between the sample space, that is set of outcomes, and a subset of real numbers. Okay, by domain, I mean that particular variable can take the values from a set of values only, and the outcome of that particular variable, whenever your occurrence happens, so the range is again within a set. As because the domain and range are bounded, so we say that your random variable establishes a relationship between your sample space, that is set of outcomes, and a subset of real numbers. Though, thus, a random variable converts outcomes into numbers. So, a definition of the, or you may say a formal definition of your random variable, it is a function whose domain is equal to set of all possible outcomes, which we define as sample space, and range is subset of all real numbers. It provides a numerical description of a random experiment. So notation of a random variable, we always denote it with capital letters such as X, capital O, and capital Z, whereas their corresponding values will denote as the small case letters, small x, small y, and small z. That is, capital X is random variable, and small x is the value that your random variable x can take. So this notation helps in distinguishing between the function and its numerical outcomes. So suppose say your capital X represent the sample space of a random experiment, and omega is the outcome belonging to your sample space. Then a random variable is defined as x of w. We say it is a function notation, x of w, and we say real number assigned to outcome w. Thus, a random variable is a function of your capital S, that is sample space, to the set of real numbers. So interpretation of your mathematical expression may go like this. So every outcome in the sample space is mapped to a real number. That means whatever is there in range, you will be finding one corresponding element in your outcome. That is the set of real numbers. And this mapping allows us to perform mathematical and statistical analysis. Hence, randomness is transformed into quantifiable values. It is a foundational concept in probability and statistics. Okay, the random variable is a function. It is having it has domain of sample space and range of set of real numbers, and there is always a mapping between S and R. So suppose say consider tossing a coin 3 times. Okay, if we are tossing a coin of 3 times, then we may have a sample space of maybe we will be getting all heads once, or maybe 2 heads 1 tail, and so on. So the sample space, that means the probability, maybe we are having 8 possible outcomes when we toss 3 coins simultaneously. Sorry, when we will be considering one coin toss 3 times. Okay, so define, suppose say we will be saying the random variable x is the number of heads. So my problem may be I will be counting, or I'm interested in the number of times that my X head appears. Okay. Suppose say my random variable X is number of heads. So I am interested in number of heads that is appearing on each outcome. So number of heads may be 0, 1, 2, and 3. So mapping of the random variable goes like this. The random variable assigns values as follows. Suppose the number of heads is 0, so x is 0. And if it is 1, then x is 1, and so on. So this demonstrates how outcomes are converted into numerical values. So over here we may have 3 heads or maybe 2 heads one day and so on. So if I will be defining my random variable as x is equal to number of heads that appear, then x may be 0 or x may be 1, x may be 2 or x may be 3 depending upon the number of heads that occur. So this is how the outcomes are converted into numerical values. So the key observations in this particular experiment, you may say the different outcomes may lead to same value of random variable. So random variables simplifies complex outcomes and it helps in analyzing patterns and probabilities efficiently. So if x and y are two random variables, then their functions are also random variables. That means suppose say their function like 2x plus 5y, xy, x square, y square, and so on and so forth. All these functions are also random variables. So which are derived from the random variables x and y. If x is a random variable, then 1 by x, 1 upon x, absolute value of x, maximum of x1, x2, minimum of x1 and x2, all these are also random variables. So functions of random variables remain random variables. Okay. So continuous functions, any continuous and increasing function of a random variable is also a random variable. So this property allows flexibility in modeling real world problems. Right? Next. So your random variables may be classified into two types. One is your discrete random variable, one is your continuous random variable. This classification basically depends on the nature of the values that your random variable takes. Okay, so by discrete random variable, I mean the random variable which can be counted 1, 2. That means they are distinctly differentiated from one outcome than the other. That is, some variables take countable values. Okay, that is number of students in a course is 50 or 60. That is my discrete random variable. Otherwise, suppose I'll take that height of a student, that or height of the students of a class, that will be in a range of values, say from 5 to 7. So that is a continuous random variable. So this leads to two types of random variables. So discrete random variable takes finite or countable values. These values are usually integers. That is maybe +1, -1, +2, -2, +3, -3, and so on. The examples of the discrete random variables may be the number of phone calls received in a day, number of road accidents occurring in a month, number of customers in a showroom at any point of time, a number of defective products, number of job applicants for a specific job role. These variables, they involve counting, means these all are finite. We can be in a position to count 1, 2, 3, and so on. So these are all examples of your discrete random variables. And One more is your continuous random variable can take any value within a given interval. So your values are real numbers including decimals. That means your continuous random variable can take a fractional value or decimal points. So your characteristics of a continuous variable is it lies within an interval such as 1 to 3, 5, 5 to 10 and so on. So infinite possible values between 2 points. Maybe, so example maybe 2.3, 5.6, 9.8 and so on. So examples may be stock markets closing prices on a specific date, temperature of a city at a specific point of time, distance traveled by a vehicle, time taken for a journey. These variables involve measurements, and these measurements are your continuous random variables. And random variables converts uncertainty into your measurable insights, forming the foundation of your statistical thinking. Next. In our real world decision making, many phenomena, including your uncertainty and countable outcomes, such as number of customers, defects, and transactions. These outcomes can be represented using discrete random variables, which take distinct and countable values. To analyze such variables systematically, we use discrete probability distributions, which assign probabilities to each possible values. That is, a random variable x converts outcomes of a random experiment into numerical values. However, knowing only the values is not sufficient. We also need to know how likely each value is. So this leads to the concept of probability distribution. Suppose say I will be checking a manufacturing lot for its defects. So I may find say 0, 1, 2. What is the probability of getting 0 defects, 1 defect, 2 defects, and so on. This leads to the concept of a probability distribution, which provides a complete probabilistic definition of my random variable x. So discrete probability distribution is a specification of all possible values of a discrete random variable along with their corresponding probabilities. Mathematically, you may say probability of, suppose say the lot with number of defects as x1, x2 and xn. It fully characterizes the behavior of the random variable. So a discrete probability distribution can be represented by using three forms. One is your tabular, one is your functional, and one is graphical. And we will be considering here in tabular as because many of the statistical analysis and all, they will be involved using your tabular and functional form, that is probability mass function. So these representations help in both computation and visualization. So suppose say tabular representation, we may have this considering a tossing a fair coin twice. So if I'll be tossing it for twice, then my x is number of heads I'll be getting, maybe 0, maybe 1 or maybe 2. So this table clearly shows how probability is distributed across. Now, so if my I have tossed the coin twice, so 0 probability of getting a 0 is 1 by 4, probability of getting a 1 is 1 by 2, and probability of getting 2 is 1 by 2. So definition of discrete probability distribution, a probability mass function is Px is equal to probability the function px is equal to probability of x taking the value small x is called a probability mass function. It assigns probability to each discrete value of x. It is the mathematical backbone of your discrete distributions. So conditions for a valid probability mass function is that px, for px to be a PMF, it must satisfy that probability mass function px is positive for all x. Okay. On the other day, we have considered, we have studied that probability of any number, any random variable is always positive or zero. It may be a impossible event or it there is every possibility of happening it. So if it is an impossible event, it is 5 and else the probability is positive. And total probability of all the occurrences is your one. Random variable, if you will be assigning several values, then probability that of each of the occurrence is equal to 1. So that means possible outcomes, the total sample space, the probability of each value in your sample space. If you will be adding up the probability of each value in sample space, then it will be equal to 1, and we call that as a subtle event. So this ensures that probabilities are meaningful and consistent. So cumulative distribution function. The cumulative distribution function is defined as the function of x is equal to probability that x is less than or equal to x. It represents that the probability that the random variable takes a value less than or equal to x. This is useful for cumulative probability analysis. Okay, and each and every distribution are having several characteristics. One of that is your expected value. And whenever we are studying or we are defining or we are making a study on a probability distribution, then we need to analyze that particular distribution by calculating certain characteristics of that particular distribution. So one of that in every distribution is your expected value, or in otherwise we call it as mean, and finally of course we will be defining that exactly expected value is not mean. So definition is, as we made it at the previously, the expected value of a discrete random variable is the weighted average of all possible values weighted by their probabilities. The formula is expectation of x is equal to small x, that is this particular random variable can take so many values. So for each value we are having, or each possible outcome is associated with a probability associated with it. So the value into the probability and added up everything is called as your expectation of x, or else we call it as weighted average of all possible values and weighted by their probability. So it represents the long run average outcomes of a repeated experiment. Okay, we are experimenting, we are repeating the experiment, we are tossing the coin once, we are getting a head is 0, the possibility is 0.5, so 0 into 0.5. Similarly, we will be adding up. Okay. So the distinction between probability mass function and cumulative distribution function, your PMF gives the probability that a discrete random variable equals a specific value, whereas your CDF, or you may say cumulative distribution function, gives the probability the variable is less than or equal to a value. Okay. Why both matters? Because they characterize discrete distribution for hypothesis testing and risk evaluation. So we will be requiring these two concepts for that. So going further detail into our expected value or mean, in probability theory, we are often interested in understanding average outcome of a random process over repeated trials. Okay, we are making repeated trials of a random experiment, and after each and every repeated trial, we are getting one outcome. So we are making it repeatedly. So what will be the average outcome of that repeated trials? That is our interest. So this average is not based on a single observation, but on the long run behavior of the experiment. Repeated trials, so long run behavior. So this concept is known as your expected value or mean. So intuition behind is that this represents the balance point or center of gravity of a probability distribution. So it tells us what value we can expect on an average if the experiment is repeated many times. It is a theoretical average, not necessarily an observed outcome. So this need to be calculated. This is one of the characteristics of any of the probability distribution, may it discrete or may it continuous. So formal definition, if x is a discrete random variable which can take the values say x1, x2 and so on xn, and with the probabilities that probability of x1 is probability x1 and so on, then the expected value of your x, that is the discrete random variable, is equal to sum of x into probability of x going from I is equal to 1 to n. So it is the weighted sum of all possible values that you will be getting in your repeated trials. Okay. So each possible value of x is multiplied by its probability. So these products are summed to obtain your expected value. So higher the probability values contribute more to the mean. Okay, thus expectation reflects both your magnitude as well as likelihood. Higher the probability, it will be contributing more to the mean. Sure. Suppose say we are having a discrete probability distribution. Consider a fair six-side die. Values 1, 2, 3, 4, 5, 6. Each value with probability 1 upon 6. So expectation of x is equal to 1 into 1 upon x plus 2 into 1 upon x and so on plus 6 into 1 upon x. So expectation of x is 3.5. So this 3.5 is not an actual outcome but an average over many trials. As your dice consists of the faces as a whole number, that is 1, 2, 3, 4, 5, 6. Though this 3.5 is not exactly an outcome, actual outcome, but it is an average over many trials. Similar is the case when you will be tossing a coin twice. Your x is equal to number of heads. So 0 is 1 upon 4, 1 is 1 upon 2 and 2 is 1 upon 4. So on average, we expect 1 head per 2 tosses. So your discrete probability distribution may have your expected value may have certain properties like linear, that is, if x is a random variable, then expectation of ax plus b is equal to a into expectation of x plus b. And if x and y are two random variables, then expectation of x plus y is equal to expectation of x plus expectation of y. Similarly, expectation of a constant is equal to the same constant. So these properties simplify your calculations significantly. Your linearity holds even if variables are not independent. Okay, for the linearity property, it it is not mandatory that your variables are to be independent. If the variables are not even independent, then too your linearity holds. So this is powerful property used in your economics, finance, and operations research. It allows your decomposition of complex problems by using your linearity. So expected value of a function, suppose say x is a random variable, g of x is a function, so expectation of g of x is equal to that x, it will be having several values, so the expectation will be like this. So used in advanced applications like your risk analysis and utility theory. And over here, let us distinguish between expected value and arithmetic mean. So arithmetic mean is computed from observed data, whereas your expected value is computed from your probability distribution. So difference, you may say your mean is sample based and your expectation is theoretical. So your expected value and the arithmetic mean are both measures of central tendency, but this describe the average outcome in a certain sense. Your expected value, it is the average value of a random variable under a probability distribution. This distribution can be either theoretical or can be empirical. This by theoretical, I mean it may be taken from your binomial, normal, or so other distributions in the context or prior knowledge. Whereas by empirical, I mean a distribution constructed from actual observed data and by taking their real frequencies, relative frequencies, etc. And arithmetic mean, as we have already discussed, key average is computed directly from the actual observed data. So it is important to be clear about what we are really asking when we pose the question. Are expected values and arithmetic mean are same, but exact conceptually they are identical? They are not, but they are not exact. Each has its own definition and purpose, but we are really exploring, or you may say, the answer to whether the two quantities, whenever you are computing arithmetic mean and expectation both of a random variable. In that case, your two quantities may be numerically equal, may not be numerically equal. The answer is maybe simply yes or no, but exactly it depends on the context in which they are used. So in real life interpretation, your expected value helps in questions like what is the average profit per transaction, what are the expected number of customers per day. It supports decision making under uncertainty. Of course, your entire probability distribution, it is for supporting your decision making under uncertain conditions. So limitation of expected value, it doesn't capture variability or risk. It is same expected value may have different distributions. Okay. Example, two investments with the same mean but different risks. Hence, variance is also important. So this may happen that you are having two investments. In both the investments, average outcome, or you may say average gain, may be the same, but with one investment you are having certain risk and with other the risk level may be higher or may be lower. So in the certain cases, in those type of cases, you will be requiring one more property you need to study for each and every distribution, and that we call as variance. And while the expected value tells us the average outcome, it is not indicating that how much the value vary. So in real world situations, variability or uncertainty around the mean is equally important. Hence, your variability, you may say, or the dispersion measures with variance are also much important. So what is exactly the dispersion? That means for each and every distribution or for each and every data set, to understand exactly the how that particular data set is behaving, only the mean or only the expectation may not be sufficient. So we need to study or we need to understand what exactly the spread of that particular data set. Okay, so dispersion refers to degree of spread or variability in a set of values of a random variable. The answers the question like how far the values from the mean. Higher the dispersion, the greater will be uncertainty. So the importance of measuring a dispersion is it helps in understanding risk and stability, essential for comparing different data sets. It is crucial for decision making in uncertain environments. So, for example, two investments may have the same mean return but different risk levels. So, concept of variance is the average of squared deviations from the mean. It measures how much values deviate from the expected value. Okay, so variance of x is x minus this particular you may say formula we have considered while calculating the standard deviation during our measures of variation. So mu is equal to mean or the expected value. P of x is the probability of the value, random value x. It gives the weighted square deviation. So interpretation of variance. If variance is small, values are close to the mean. If the variance is large, values are widely spread. So it reflects the degree of uncertainty or risk. The more the spread, more the variation, more is the uncertainty. So standard deviation, it is square root of your variance and it expresses dispersion in the same units as the variable. So why standard deviation is preferred? Variance uses squared units, which is less intuitive. So standard deviation brings back original units, easier to interpret and communicate. So variance versus mean. Mean is your central tendency, variance is spread around the mean. Together they provide a complete picture of the distribution. So while studying each and every probability distribution, we need to study the mean or you may say the expectation and variance of each and every probability distribution, which will give us the entire picture of that specific distribution. So concept of risk and variance in finance and business. Variance is used to measure of risk. Higher the variance, higher is uncertainty, higher the potential fluctuations, lower the variance, more stable is your outcomes. So now we will be discussing certain types of discrete probability distributions. So discrete probability distributions describe random variables that take countable values. Okay, among these, three fundamental distributions are widely used. One is Bernoulli, one is binomial, and one is Poisson. So we will be discussing these three in detail along with their expectation and variance. These form the foundation for modeling real-world discrete events. So the relationship, if you consider, you may say the Bernoulli is leading us to binomial and it will be leading us to Poisson. Your Bernoulli is based on a single trial, whereas your binomial is based on repeated trials, and your Poisson distribution is basically for rare events over time or space. Each builds upon the previous concepts that we have studied. The concept you may say the simplest Bernoulli distribution, which is the simplest of your discrete probability distribution. It represents an experiment which will be having only two possible outcomes, maybe success and failure. The success over here is represented as 1 and failure as 0. The example you may say your coin toss, it has got only two possible outcomes. One is either head or tail. If you are getting a head, it is success. If tail, it is failure. So definition, a random variable x follows a Bernoulli distribution if x is equal to 1 with probability p and x is equal to 0 with probability 1 minus p, where p is a number between 0 and 1. The p is the probability. Okay, so if we will be representing the Bernoulli distribution with a probability mass function, it goes like this. Probability that x can take the value of x is equal to p to the power x into 1 minus p to the power 1 minus x, where x can take only two values, maybe 0 or 1. That is p probability of x is equal to 0 is p to the power 0 and 1 minus p to the power 1 minus 0. That is 1. 1 minus p to the power 1. Okay. So this compact formula represents both outcomes. So the expected value of your Bernoulli random variable x is expectation of x is equal to p. So how come we arrived at this? This is a simple calculation. This is because for a Bernoulli distribution, your random variable x can take two values. One is x, 1 and one is 0. So probability that x is equal to 1, if it is equal to p, then probability that x is equal to 0 is 1 minus p. That is, we define it as q. Okay, so we find expectation of x as we study probability that x is equal to 1 into the 1 and probability that x is equal to 0 into 0. So p into 1 plus q into 0 is equal to p. This is how your Bernoulli's expected value can be calculated. So expected value of Bernoulli random variable x is equal to p. And variance of a Bernoulli distribution x is pq, that is p into 1 minus p. How can we calculate that? It is expectation of x square. Let us first find out expectation of x square, that is equal to probability that x is equal to 1 into 1 square, probability that x is equal to 0 into 0 square. Over here p into 1 square plus q into 0 square, that is equal to p is equal to expectation of x. Okay, so variance of x is expectation of x square minus expectation of x whole square. Okay, that is p minus p square, that is p into 1 minus p, that is equal to pq. Right? So with this result, it is easy to prove that for any Bernoulli distribution, its variance will have a value inside 0 and 1 by 4. PQ means 1 by 2, 1 by 2. If I am tossing a coin, probability that I'll get a head is half and probability that I'll get a tail is half. So P and Q is 1 by 2, 1 by 2, 1 by 4. So its variance will have a value inside 0 and 1 upon 4. So mean is equal to probability of success and variance depends on success and failure probabilities in case of your Bernoulli distribution, right? So next is your binomial distribution. So it is just an extension of your Bernoulli where that is based on a single experiment or single trial. Over here it is the Bernoulli extended to multiple independent trials. It counts the number of successes in n trials. Suppose a number of heads in 10 coin tosses. Okay, conditions of binomial distribution. A random experiment follows binomial distribution if there are fixed number of trials, say n, and each trial has two outcomes, success and failure, and probability of success is constant, and each and every trial is independent, and hence the trials in your binomial distribution are called as your Bernoulli trials. So over here, the mass function is follows this formula, that is probability that x is equal to x is ncx, okay, into p to the power x into 1 minus p to the power n minus x. So where n is number of trials, x is number of successes, and p is probability of success for x is equal to 0, 1, 2, and so on n, where your ncx is equal to factorial n. By factorial n, I mean factorial n is equal to n into n minus 1 into n minus 2 into n minus 3 and so on into 3 into 2 into 1 divided by factorial x into n minus x factorial. The formula of factorial goes like this. Means if it is n factorial, means n into n minus 1 into n minus 2 and so on into 3 into 2 into 1. And if it is x factorial, then s. In the same fashion, x into x minus 1 and so on 3, 2, 1. Okay. So cumulative distribution function in case of your binomial distribution is denoted as this summation I is equal to probability that x is less than or equal to x, I is equal to 0 to x, nci p to the power I 1 minus p to the power n minus I, where x is the floor under x, that is the greatest integer less than or equal to x. Okay. So expected value and variance, if x is equal to x follows a binomial distribution with n trials and p as its probability, that is x is a binomial distribution, distributed random variable, n being the total number of experiments and p the probability of each experiment, yielding a success result, then expected value of x is expectation of x is equal to np, and variance of x is npq. This similarly follows from the fact that variance of a sum of independent random variables is the sum of the variances. Mean increases with number of trials and variance reflects the spread of the outcomes. So next is your Poisson distribution. In many real life situations, events occur randomly and infrequently, such as accidents, system failures, or incoming calls. These events can be predicted exactly but can be studied in terms of average occurrence over time or space. The Poisson distribution provides a powerful model for such phenomena. So when to use your Poisson distribution? When the Poisson distribution is appropriate, events occur independently, events occur randomly over time and space, and the average rate of occurrence is constant and it is denoted by lambda. Two events cannot occur simultaneously in this case, and it is ideal for modeling rare events. The number of calls received at a call center per minute, number of accidents at a traffic junction per day, number of defects in a production batch, and so on. A random variable x follows a Poisson distribution if it represents the number of occurrences of an event in a fixed interval given a constant average rate. So lambda is equal to average number of occurrences. This is the only parameter in your Poisson distribution, that is lambda. And this Poisson distribution is the probability mass function is lambda to the power k e to the power minus lambda and divided by factorial k, where k is the number of occurrences which can take values 0, 1, 2 and so on. E is the Euler's number that is equal to 2.71828 and so on. And as usual, your k factorial is k into k minus 1 and so on. So the positive real number lambda is equal to the expected value of x and also to its variance. Lambda is equal to, that means in case of your Poisson distribution, your expected value and variance both are equal, and that is lambda. And cumulative probability is x less than x or x greater than x, and these are obtained by summing individual probabilities. And whenever your n is large and p is small, binomial distribution approximates Poisson and simplifies complex calculations, derivation ideas. That is, when your Poisson distribution arises as a limiting case of binomial distribution when your n tends to infinity and probability approaches to 0. It maintains a constant mean, that is lambda is equal to np. So mean is, and variance in the, you can remember one thing, that in case of Poisson distribution, your mean is equal to variance and it is cubed for small lambda. It is defined for x is equal to 0, 1, 2 and so on. So customer arrivals in a service system and so on, these are the applications. And advantages, you may say, it is simple, easy to apply, suitable for rare events. Limitations may be not suitable for high probability events, as because it assumes a constant rate. So your Poisson distribution transforms randomness of rare events into a structured and predictable framework for analysis. So this is a simple comparison between the three distributions that we have just discussed. In case of Bernoulli, your mean or expectation is a P. In case of binomial, it is NP, and in case of Poisson, it is lambda. And probability function, it is P is success, 1 minus P is the failure. It is combination of P and F, that is probability mass function. And in case of your Poisson distribution, your mean and expectation and variance are one and the same, whereas in case of Bernoulli, it is P and P minus PQ, it is NP and NPQ. And typical use cases, Bernoulli is used in case of the decisions where it is the outcomes are only 2. In case of binomial, the outcomes are 2 but repeated trials, and in case of Poisson, it is rare events. Comparison, you may say the single trial, multiple trials and rare events. Bernoulli is the building block, binomial is the repetition, and Poisson is its real world approximation for rare events. This, you may say, it is conclusion of it. Practical takeaway, you may say, use the right distribution to count events, evaluate outcomes and make better informed decisions from data. So this is the summary, and you will say, thank you. Understanding probability empowers us to make informed decisions in an uncertain world. So to survive in this uncertain world, how can we take the appropriate decision with the outcome available? This is the probability and probability distributions that supports and empowers. Thank you.